All right, so we're still on 8.3 here. We're looking at a different application of integrals. This one involves what are called moments and center of mass. So to introduce this idea, we're specifically going to be looking at objects that we can think of as thin plates. Kind of like with the hydrostatic pressure stuff that we did in the previous couple of videos. We were imagining like a thin plate submerged in water. This time we're not dunking this in water, we're just looking at the plate itself, and we're specifically trying to find a point that we can balance that plate at if we've placed it on a fulcrum. So this is something that you've probably seen, just in other contexts before. You have those guys who are able to like stack oddly shaped rocks so that everything balances in a really cool way. What they're doing is they're using the idea of center of mass. So basically the idea is that there is a unique point on a plate like this where if you place this fulcrum exactly at that point, it'll balance. It's not going to tip one way or the other. And that point is what we call the center of mass or the center of gravity for that plate. Now, I keep using the term plate here, but we're going to be using a specific word in place of that. We're going to use the term lamina. So you'll see that come up over and over again. When I use the word lamina, I'm talking about a thin plate like this. Okay? So in order to, it's going to take some work developing a method for finding this point. So to do that, we're going to start in a much simpler scenario. Okay? We're going to think of things in one dimension to start. So imagine that you have a fulcrum like this, so something that we can balance a rod on at a single point right here. And imagine that we place this rod there and that the rod has negligible mass. The meaning of that is that we don't want the mass of the rod to influence what's happening with the masses that we place on it. So we're kind of imagining the rod as having a mass of 0, even though that's not really what would happen in reality. Then on that rod, we're going to place 2 masses, something that we call point masses. So again, this is not something that really exists in reality, but by thinking of things in ideal circumstances like this is going to help us with the more practical stuff that we're doing later. So you're going to imagine a single point that has a certain amount of mass, and all the mass is concentrated on that point. M1 for the first one, M2 for the second one. Okay? Now, there is a principle that goes all the way back to Archimedes of Syracuse, ancient Greek mathematician, that we call the law of the lever. And basically what it says is that if this rod is balanced, then the product of the mass M1 with its distance to the fulcrum, which we're going to call D1, has to be equal to the product of the mass M2 with its distance from the fulcrum, which we're going to call D2. Now, this is actually pretty intuitive, again, just from, life experience. So, for example, if this fulcrum was completely in the center, like right in the middle of this rod, then in order to be balanced, we know that the 2 masses would have to be the same. And in that case, M1 times D1 and M2 times D2 would be equal to each other because the masses are equal and the distances are equal in that scenario. However, if we suppose that mass M1 is heavier than the mass M2, then placing this fulcrum in the center would cause this side to dip down. It would become unbalanced and it would lower on this side, raise up on this side. We know from just kind of experience and feeling things out as human beings, that if you have that unbalanced larger mass here and smaller mass here, moving the fulcrum closer to the heavier mass will actually give us it'll approach something that's more balanced. And eventually you can find a point where even though this mass is heavier than this one, relocating that fulcrum closer to the heavier mass will balance things out. So what's happening is if you have a large mass here, we want a small distance here. And with the small mass here, we want a large distance here so that the products of them can be equal. Okay, that's the underlying idea there. So now, here's what we want to do. We want to impose a coordinate system on this thing right here. Okay, so the idea is that we want to create a one-dimensional coordinate system where I'm going to put 0 all the way to the left past this mass M1 right here. And then if I kind of extend this thing this direction, I want to find locations on my coordinate system for kind of the relevant values here. So M1, I'm going to say that it's at the coordinate x1 right there. The fulcrum, let's put the fulcrum at x bar. So that's going to represent kind of the balancing point or the center of gravity. M2, let's suppose it's at the point x2. Okay, my purpose for doing that is because now that I've imposed a coordinate system, I can talk about these distances in terms of these coordinates. So D1 would have to be x bar minus x1. You're seeing that right here. D2 would be x2 minus x bar, which is here. Okay, now assuming that things are balanced here, so that the fulcrum is at the center of mass or center of gravity of this system of masses here, we can substitute D1 in for our formula up here, or our equation up here. We get m1 times x bar minus x1. On the right side, we plug in d2, giving me m2 times x2 minus x bar. Then we're going to do a little bit of solving. The goal is to solve for x bar, because x bar represents our center of mass. Distribute the m1s in. Collect any terms that have x bars in them on one side of your equation. Everything else goes to the other side, and we end up with this here. Factor that x bar out on the left-hand side and divide by the m1 plus m2 that would appear in parentheses there, which is why that's showing up in the denominator. So what this is showing me is that x bar, my center of mass in this 2-point mass one-dimensional system, is this. m1 times x1 plus m2 times x2 divided by m1 plus m2. Now, there's a simpler way of understanding what we're looking at here. So first of all, these values, m1, x1, and m2, x2, are specific quantities that we call moments. Specifically, it's the moments of the masses m1 and m2 respectively. So m1 times x1 is by definition the moment of the mass m1, and then similar for m2 there. Okay. Down below in my denominator, I can see that I have the sum of the masses in the system. So I can think of that denominator as like the total mass of the system. Okay. So phrasing things differently, the center of mass of this system that we have up here is equal to the sum of the moments of the masses divided by the total mass of the system. Now, we did a derivation where we had 2-point masses, but the same results will actually still apply if we put several point masses all along this rod. So if we have a total of, say, n masses, m1 through mn, and let's suppose that in our coordinate system up there, they're located at the points x1, x2, all the way up through xn, then the center of mass is found in a way that kind of generalizes this result. We get the sum of the moments, which is that summation right there, for each of our masses, divided by the total mass. This sum is adding up all n of those masses, which is the total mass of the system. We're going to call that sum down there just little m. It represents the total mass. So x bar is equal to the sum of the moments divided by the total mass of the system. Okay? Now, as interesting as all of that is, we're still just talking about a one-dimensional system of masses, which is not what we typically look at in reality. So we want to bump things up a dimension and think about what this would look like in a two-dimensional system of masses. So how do we imagine that? Well, now what we're going to do is imagine that we're in the plane. Okay, so here's the diagram we're working with. And in the plane, we want to have, again, n different masses that are all concentrated at single points in the plane. Okay, so let's suppose that those points are located at x1, y1 for the first mass, x2, y2 for the second mass, and so on, all the way through xn, yn for the nth mass. Okay? Then we're going to define moments again, but this time we're going to define them relative to our coordinate axes. So first of all, starting with the moment about the y-axis, we define the moment about the y-axis, which we use capital M and a subscript of y, so my, to represent that, as the sum of these values here. The sum of mi times xi, where I goes from 1 to n. Now, why would we define that this way? It may seem odd to you that we're calling this my, but we're not seeing any y's appear here. We're seeing x's. The reason for that is because if you look at this diagram, I have three masses in this picture. The x1, x2, and x3 are the x coordinates of each one of these. But if you notice, those x coordinates also give me the distance between each of those masses and the y-axis specifically. So you can always think of an x coordinate as a distance, which you can kind of have, you have to have an interpretation of negative distance there for that to make sense, because this is a negative x value here. But it's the distance from a point to the y-axis. That's how we can think of that. Okay, and that fits with how we were thinking of moments before. We wanted those distances to be, we wanted those moments rather to be a mass times a distance. So similarly, the moment about the x-axis measures or uses the distance from each of our point masses to the x-axis, but that's exactly what the y-coordinates of those points are doing. So mx is defined to be the sum of all of these miyi's, where I goes from 1 to n. So again, this is something that's going to confuse people, but if you think through the reasoning behind it, there's a reason why this subscript does not match the variable that actually shows up in the theorem, or in the definition rather. Okay. Now, what do these values tell me? Well, what they tell me is the tendency of our system of masses to rotate about whichever given axis we're talking about. So suppose for a moment that, again, we're in the plane. You can imagine this as like a big board that's, you know, large enough to rest these masses on. Maybe like a big piece of plywood or something. And then suppose you put that piece of plywood, we're going to assume it has negligible mass, so it has like a 0 mass, and you place it on like a narrow rod aligned with the y-axis, right? And then it's got a balance. So if it's unbalanced, it's going to shift, it's going to rotate about the y-axis that way or that way. You place these masses on here, and if you look at these moments, it's going to tell you the tendency of the board to rotate about that axis. So if we get a positive moment here, it's going to have a tendency to rotate into the positive side of the y-axis, the quadrants 1 and 4. Similar for negative, it would rotate this way. That's kind of the idea. Okay. We know from kind of generalizing our previous results that the center of mass of this system is going to be located at the point x bar, y bar, which is where x bar is going to be equal to the moment about the y-axis, my, divided by the total mass of the system. Y bar is equal to the moment about the x-axis divided by m. Okay, these together give me the coordinates of my center of mass. So let's do an example similar to the scenario we've presented here, where we have three masses and we want to find the center of mass of that system. So it says find the center of mass of the system of objects having 3, 4, and 8 as their masses located at these 3 points here. Okay, and I do have a picture which shows where the center of mass is. We're going to talk about that once I get my answer here. But let's see if we could work this out. So up here, I'm looking for x bar and y bar. Those would be the coordinates of my center of mass. There's a couple of things I need to compute first. I need my, mx, and I need lowercase m. I'm actually going to find lowercase m first. It's the sum of the masses in the system. 3 plus 4 plus 8. Okay, that's equal to 15. So I know that the total mass in our system is 15. I'm just getting that from these values here. Next up, we want to find mx and my. Let me go ahead and find my first. Here's our formula for my. It's the sum of the products of each mass with the x-coordinate of the point that that mass is located at. So we have a mass of 3 located here. Its x-coordinate is -1. 3 times -1. And then I have a mass here of 4. Its x-coordinate that it's located at is 2. So that's going to be plus 4 times 2. And then I have 8, a mass of 8. The x-coordinate of its location is 3. Plus 8 times 3. Okay? So that's -3 plus 8, which is 5 plus 24, that's 29. Okay? And then I have mx as well, same idea. Even though there's an x here, we're using y coordinates. So same idea, 3 is my first mass, but times the y coordinate of that point, 1, plus 4 times the y coordinate of this point, -1, plus 8 times the y coordinate of that point, which is 2. That's 3 minus 4, which is -1, plus 16, which would be 15. Okay? So what this means is that my x bar is equal to my over little m, which is 29 over 15. My y bar is equal to mx over little m, which is equal to 15 over 15, or just 1. So that my center of mass is the point 29, 15, 1. Whoops. I keep doing that where I go off the screen. Okay. Now, if I were to look at where that is graphically, here's those 3 point masses at their given locations. 29 is very, very close to 30. So if it was 30, and 30 divided by 15 is what I would have here, that would be 2. So my center of mass is very, very close to the point 2, 1, but just a little bit to the left of that, since that's actually less than 2. That puts the center of mass right where that red dot is. I want to think of this in logical terms. If you measure the distance from your red point to each of your point masses, it is closest to the largest mass. It's closer to 8 than it is to either of these other two values. And it's furthest from my smallest mass. Notice it's 1, 2, 3, almost 3, because it's not exactly on that intersection of grid lines there, but close to 3 units away from 3, and it's more like 2 units away from 4, close to 2. So that jives with the way that we've been thinking about these systems in the one-dimensional case. Remember how we had this whole discussion? If the M1 is a larger mass, then the distance between my fulcrum and that has to be shorter, whereas the distance from my fulcrum to the lighter mass or the smaller mass should be longer to balance these. It's the same idea, but we're seeing it here in 2 dimensions now. Okay? All right. So that's nice, that's cool, but it's not really the scenario that we're interested in. Because where this all started was trying to find the center of mass of a lamina or a plate. That's an entire region which contains infinitely many points, not just 3 points like the previous example. So we need to now take the results that we just came up with and try and adapt it to the real thing that we're after, which is the center of mass of a lamina, which we're going to think of as the center of mass for like a plane region. Okay, so if we have a flat plate and it has uniform density rho, which means all throughout the plate, that's what this region is going to represent here, all throughout that plate the density is not changing, it's uniform, then we should be able to come up with a way of finding the center of mass of this plate. In the case where that density is uniform, that center of mass has another name. It's called the centroid. And this is a geometric term, but it's the exact same point that the center of mass will be at. Now, there is a different scenario that we could look at, which is if the density of this plate is not uniform. So if it varies throughout the plate, In those cases, the center of mass is not necessarily the same point as the centroid. So in the most general case, we actually can't think of these two terms as synonyms, but for the types of problems we do in 8.3, they are. The approach that you would take if the density of our plate is not uniform is a subject that you don't talk about until Calculus 3, because you need double and triple integrals to do that, depending on whether this region is two-dimensional or three-dimensional. So don't worry about that now. That comes later. What we need in order to derive the result that we're talking about here are three physical principles. And I'll mention when they come up in the derivation, but we have, first of all, the symmetry principle. This is the one that states that if a region is symmetric about a line L, then the centroid of that region has to lie on L. And this specifically implies that the centroid of a rectangle is its center. That's the main reason we want this result. So here's a way of picturing that. Imagine I have this rectangle, right? I have a couple of lines of symmetry that I could look at. First of all, if I put a vertical line right down the middle of that rectangle, then the rectangle is symmetric about that line. So the symmetry principle tells me that the centroid has to be on that line. And kind of the basic reason that's the case is because the left side of the line will have the same area as the right side of the line. So that the area, which we're also going to be kind of thinking of as mass in a certain sense, is evenly distributed on either side of that line. Now, there's another line of symmetry I could consider, and that's if I put a horizontal line through that rectangle, right through its center, right through its middle. So this and this are mirror images of each other. This rectangle is also symmetric about that line. That means that the centroid has to also be on that horizontal line. There is only one point that's on both of those lines, and that's the exact center of the rectangle. So by this principle, the center of the rectangle is the centroid for this rectangle, okay? So we're going to need this specific result in our derivation. Second, if the mass of a region is concentrated at its centroid, then the moments will remain unchanged. So remember, in our previous example, we were thinking of the system of point masses as each having their own moment. Now there's an infinite number of points in this rectangle. So they each have their own individual moments. And what we're doing is we're thinking of instead of having the mass spread out over this entire rectangle, if we shrink the mass down to a point so that this centroid has all of the mass of this rectangle in just that single point, the moment of this rectangle is not going to move by reconcentrating the mass there. The moment of this rectangle will remain where it is, okay? Finally, the third principle is that the moment of a union of two non-overlapping regions is equal to the sum of the moments of the regions. We're going to use rectangles with that idea. So if I were to take two rectangles, maybe of different sizes or whatever, and put them side by side, each rectangle has a moment that we could assign to it. When I take those two rectangles and put them together and consider them just one region now, the moment of that region that I've created is the sum of the moments of the two pieces that I used to put it together. That's what this third thing is saying. So again, when we get to the place where I need these principles, I'm going to mention them. All right, now we want to find the center of mass or the centroid of a region in the plane, which is going to be denoted by this fancy R right here. And remember, we call these things laminas. So let's suppose that our lamina occupies the region that's below this positive function y equals f of x. We're assuming our curve is above the x-axis for this. And it's bounded below by the y-axis, and on the left and on the right by these two vertical lines, x equals a, x equals b. What we're going to do, as you've seen many times now, is we're going to take this interval ab, and we're going to cut it up into subintervals of equal width delta x. So here's your subintervals. Okay, there's n of them all together. And then I'm going to let xi bar represent the midpoint of each one of those subintervals. Okay, so you're seeing all the subintervals down here. As we've done with like the midpoint rule for approximating definite integrals. We're going to construct rectangles over each one of these sub-intervals, and using the midpoint. The midpoint of each subinterval is going to be plugged into our function to determine the height of each one of these rectangles. The goal is to just find the centroid of each individual rectangle to start. As we've seen over here, the center of a rectangle is its centroid. That's from that first principle. So if I'm looking at my ith rectangle right here, I want the coordinates of that centroid. Well, the x coordinate would just be x bar, because remember, x bar is the midpoint of that interval, so that would be right in the center. The y coordinate is basically the distance from that point to the x-axis, which is half the distance from the x-axis to the top of my rectangle. That, or let's call that height instead of distance. That height would be f of xi bar. So the centroid is going to have a y coordinate that's half of that, 1/2 times f of xi bar. So we have the location, we have the coordinates of the centroid of our ith rectangle right here, okay? Now, the area of our rectangle is equal to f of xi bar times delta x. That's the height of my rectangle times the base of my rectangle. And remember, if we want to find the mass of an object, of like a two-dimensional plane region, then it's the density times the area. So the mass of that rectangle is rho. Remember, we're assuming that that's the density of this region, times f of xi bar times delta x. Okay? Now, the next thing I want to do is find the moment of Ri, my ith rectangle, about the y-axis, and then we'll do it about the x-axis as well. And what that's going to be defined to be is the product of the mass of Ri times its distance to the y-axis. Remember, we use those distances in our moments, the mass times the distance. So if you look at this point, its distance to the y-axis is exactly what the x-coordinate of that point is, xi bar. Its mass we found here. So the moment of Ri about the y-axis is this, which simplifies to rho xi bar times f of xi bar delta x. Okay? This is a long derivation. I know there's a lot that goes into this. So if I wanted to now take my moment for that rectangle and use it to determine the moment of the entire plane region that we were talking about originally, about the y-axis, then I would go and find the moments of all n of those rectangles. And here's where we're going to use this property right here. So the moment of the union of two non-overlapping regions is the sum of the moments of those regions. So if I were to find the moment for all n of these rectangles, I could add all n of those moments up, and that would give me the moment of the entire union of all those rectangles, this whole region, just by using that principle. Okay? So I can see that approximation gets better and better if I give myself more and more subintervals. So we take a limit as n goes to infinity, and now what I can do is define the moment of my entire plane region R about the y-axis as the limit of the sum of those individual moments, which is going to lead me to a definite integral, because this is a Riemann sum. Rho times the integral from a to b of x times f of x dx. Okay? I can do the same sort of derivation for finding the moment of my ith rectangle about the x-axis. This time, the distance from the point to the x-axis is the same thing as the y-coordinate of that centroid, which would be 1/2 f of xi bar. So I get a similar formula, but that's a key difference. Is instead of multiplying by xi bar here, I'm multiplying by 1/2 f of xi bar, which gives me rho times 1/2. Notice there's an f of xi bar showing up in two places here, and everything's being multiplied. So I get f of xi bar squared delta x there. Once again, take a limit as n goes to infinity as we sum these for all n of our rectangles, and I get this definite integral after doing that. I get rho times the integral from a to b of 1/2 f of x squared dx. Okay? Those are the moments. What we need, though, is the center of mass. And remember, the coordinates for our center of mass, x bar and y bar, come from dividing our moments by the total mass of our system. Well, the mass of our plane region would just be the density times the area of that region. And because that region was an area under a curve, I can use the definite integral from a to b of f of x dx to get that area. So rho times that definite integral is my mass. Now look at what happens. X bar is equal to my over little m, which we have my here. We showed that up above, how we got that. And here's little m, which we just found here. The rows here end up canceling each other out. And then I get this integral from a to b of x, f of x dx, over this integral representing the area of the region. Similar thing happens down here for our moment, or for our y coordinate of our center of mass. Our moment about the x-axis over the total mass gives us this, the rows cancel out, and I get this. Okay, now, that's important because the rows canceling out means that I never needed to know what the density of our region was in the first place, or the density of our lamina, because in order to find the center of mass, they cancel out of the computation and never really factor in anyways. I'm going to write this in a simpler form, remembering that the denominator of each one of these is just the area of our region. Let's call the area a capital A. So each of these can be written by instead saying 1 over A times this integral gives me x bar, 1 over A times that integral gives me y bar. Okay, this video has gone on a little bit longer than I wanted it to go, so I'm going to stop here, but then we'll look at some examples in the next video.